Good afternoon, good morning, and good evening from whichever part of the world you are. I'm Veda, and I'm from the Sensors Council, managing the Chapter Engagement Committee. Today, here we have gathered for the first webinar from the MEMS cluster, and the first speaker is Professor Deepak Uttamchandani. I'll give you a brief introduction about him before I hand over the stage to him. Deepak is Emeritus Professor at the University of Strathclyde, Glasgow, United Kingdom. He founded the Center for Microsystems and Photonics at University of Strathclyde in 2000 and led this research unit for over 20 years. His research interests are in devices, sensors, and instrumentation based on optics, photonics, and MEMS technologies. He has co-authored over 320 research publications and edited 4 books. He was the founding editor and first editor-in-chief of IET Micro and Nano Letters, a journal dedicated to research in micro and nanoscale technologies. Currently, he is associate editor-in-chief of IEEE Sensors Letters, a journal dedicated to rapid publication in the field of sensors technologies, and sensor networks. He is IEEE Life Fellow for contributions to photonics-based sensing. He was awarded the 2024 IEEE Joseph F. Award in Instrumentation and Measurement for contributions to photonics-based optical frequency and wavelength domain instrumentation and measurement, being the first fellow of Indian heritage to receive this prestigious IEEE award. He also received the IEEE Sensors Council Technical Achievement Award in 2017 for contribution to photonic and fiber optic sensing system, which has led to significant improvements in healthcare. He is currently also the president of Sensors Council, and that's why we thought this is the best way to start the webinar series from the MEMS cluster. Thank you, Deepak, for accepting our invitation, and now it's off to you.
Okay, thank you very much. Yes, it's an honor to be here for all the reasons you have said. As Vida said, I've spent all of my career working in photonics, optics, and MEMS, and kind of fusing these three technologies in the way I'm going to describe to you. So my talk is titled Foundry Fabricated MEMS for Photonics. And just to confirm what Vida said, I'm based at the Center for Microsystems and Photonics, which I founded. We're at the University of Strathclyde, which is in the city of Glasgow. So before I proceed, I just also want to extend my thanks to everybody who has been involved in setting up this webinar. I know there's a lot of coordination and everything like that to take place. So I appreciate the work that everyone has done to bring us to this stage. Okay, so let's now move into the talk itself. What I'm going to do in this first slide is presenting the context and organization of this talk. And what I'm showing you there is something that many of you may recognize. It's that many research institutes and labs, which include my own, do not have the costly and sophisticated facilities needed to fabricate advanced MEMS. So they are fabless in this sense. In my own university and many other places I've been, there are small-scale MEMS fabrication facilities, but it's hard to keep them modernized and fully up to date because that's a very, very expensive process. So how do you conduct MEMS research and contribute to the discipline if you don't have an extensive MEMS facility at your disposal? Well, the answer, or at least one answer, is by using so-called MEMS foundries. MEMS foundries are out there in the world. They're commercial organizations providing MEMS services, MEMS fabrication services mostly. So I'll start by making a few general observations about using foundries based on our over 20 years experience. In fact, I think it's like 24 years experience with MEMS foundries. I will give you some examples of our MEMS research using these commercial foundry services, particularly the MPW. I hope by now the majority of you know what MPW means. It's multi-project wafers. I will then make this point to you that when you use MEMS foundries and MPWs, you need to have imagination and creativity. Why? Because we are all trying to achieve something unique, different, something publishable, but we are all starting from the same basis. We have the same tools. So if we all have the same tools, how do we differentiate what we're doing from what other people are doing who have exactly those same tools? So you need to be creative, you need to be imaginative, you need to be bold in order to move forward. Then finally, I'll make some wrapping up observations about our own experience, and then we can go into questions and answers. Okay, so now everyone here knows what MEMS are. Okay, so it's applying the processing technologies of the semiconductor industry to create these micromechanical devices and systems. And why do you create them? For this reason, that there are numerous applications of these devices. These are just some of the examples. In sensing and instrumentation, you have these devices. In communications, RF, switches, resonators, impedance tuning, photonics, so many applications in comms. In transport, all the vehicles, most of us travel in nowadays, you have accelerometers, pressure sensors in your vehicles. These are all MEMS-based products. In aerospace, you have MEMS devices for guidance and navigation. In medical technology, you have. In life sciences, you have. And so there are many papers out there that describe these applications. So I don't want to focus too much time on that, just to remind you that the applications are quite diverse. Okay, so what has been our experience with using MEMS foundries? These may not apply to every single person, but this certainly is how I think about it. So if we look at the plus sides, the advantages of doing this, then we see that the foundries provide to you a reliable process technology, which they have already developed. They have invested the money and time to make sure that these technologies are available to us as the users. So that technology is already readily available. You can get access to a range of technologies from different foundries. So each foundry has its own specialization and skills. And so you can go to different foundries depending on what particular designs and ideas you have. Third is that you generally get rapid turnaround, and that's because you're not developing a process. The processes have already been developed. Fourth, you get cost-effective prototyping with multi-project wafers, okay? And that's very important, especially for people like us. We are in universities. We don't have access to those huge resources that commercial firms have. So multi-project wafers is a cost-effective way for us to progress in this field. Fifth, you can do post-processing of foundry devices. And we have done this, and many others do this. So we receive our devices from the foundry, then we add extra value to these devices. You might add some special material. You may do something extra to take your device and give to it some novel or innovative functionality. So that is within your control. Then going through the foundries, you have a clear route to manufacture. If you really want to start manufacturing, then working with a foundry gives you that option more readily. And finally, if you're a startup company, you want a low-cost approach to starting up, then going to foundries, working with them on even with multi-project wafers, you can negotiate with them, and this is a good way to move forward. So the one main disadvantage I'm showing over here is that with foundries, you usually have fixed processes because they have spent lots of money, lots of time to optimize their processes. Now, if you come along and say you want to change this, you want to change that, generally speaking, they will not be receptive to you. So that is something you have to bear in mind when you're trying to go down this route. So here are some illustrations of devices that we have worked with for many years. And these are actually using different processes. So here on the first diagram here, these are all scanning electron SEM images, okay? This is a very interesting device. It's what we call a latching RF switch. And what's going on here? So RF is radio frequency. And this side of the image over here, where I'm showing you, this is a RF waveguide. In fact, it's a microwave waveguide. It's of the GSG configuration, meaning ground signal ground configuration. So through this center channel over here, microwaves will travel. Now you can see what we have designed over here. We have designed this break in the waveguide, or we have designed this break which is connected to this mechanical system over here. And the idea is that I can use these micro actuators, all these MEMS devices, and I can pull this structure to the left. If I pull this arrow-shaped structure to the left, then you can see that this waveguide is interrupted and the signal flow will stop. If I push this arrow structure to the right, then this arrow fits into this gap, and then there is good continuity and the signal will transmit through. Important thing here is that this movement is handled by these micro actuators. This design is called a chevron micro actuator, and it pushes structures to the left. These are also chevron micro actuators. And if you can see here in the center, we have teeth. And these teeth lock the actuator into position in either the on position or the off position. So that's one example of a MEMS device. And then going around these other images here, this is a micro mirror. This is made out of the polysilicon process. This is a really complex structure. It has got springs. The structures here are springs. It's got hinges over here. This circular piece over here, this is a reflective structure. So this is in fact a movable micro mirror. And I'll talk about that a little more later. Down here, the third image over here, this is built on SOI, silicon on insulator. And this is like an active device, which is like a chassis. It means in this gap over here, I can put maybe a micro lens, I could put a ball lens or a microspherical lens. And by operating these actuators, I can move this lens up and down by small distances. And that allows me to focus and defocus. And this last structure here is, again, a complex structure. We call it a lifting platform. If you look at it, in the center, there's a platform, and I can place an object on it. And these four structures around the side, these are actuators that push inwards. And if I push these actuators inwards, then you can imagine how this platform rises out of the plane and it lifts up. So I can lift small objects by using this technology. Okay. So let me describe the first of the three processes I want to discuss with you today. And this is about the polysilicon process. In the past, when we were using it, it was called the poly-mumps process, but and it was provided for us through the MEMS cap Foundry based in the US, but it has been taken over, and the new owners, who are the Science Foundry, call it the polysilicon process, but it's essentially the same. So I don't want you to focus on all the details over here because it's a complex structure, but just bear in mind that in this process, we have three polysilicon layers, okay? What's called poly 1, no, poly 0, poly 1, poly 2, that's three layers. We have deposited oxides, which are sacrificial, so that's the oxide layer there. We have silicon nitride, which is the black layer here, which isolates the device from the underlying silicon. We also have metal. So this is our toolkit. So what do I have in my toolkit? I have in my toolkit these 8 layers, 7 layers, and not 8, 7 layers. And I have the ability and creativity to do something with these 7 layers, how to design with them. So what can I do with them? So let me show you first device we have. This is a device which is a micro actuator. It's called the SDA, a scratch drive actuator. So first I'll turn your attention to the right-hand side of this slide. And in fact, these two pictures are the same, except the lower picture is in color to make it a little clearer. And what I've done is I've designed this device over here, and you can see the corresponding layer. So we have parts of the device called clips. They are made in poly 2. We have this gray plate, which is also poly 2. We have bushing, and I'll explain that to you. And we have the sliders, and we have the rail, which are in poly 1 and poly 0. So these are all the layers of the polysilicon process, okay? What is this and how does it work? So it's an actuator, a micro actuator. And the right hand here shows you, the left hand here shows you what it is. So here is the silicon substrate. This gray represents the insulation, which is the silicon nitride dielectric. And this L-shaped piece over here is also polysilicon, okay? And if you look at it, this is like a capacitor, because if I apply a voltage between the top and the bottom, the top may have a positive charge, the bottom may have a negative charge. And what happens? If you have a positive and negative charge, they attract towards each other. So it means that this very thin bit over there is attracted to the bottom and it bends downwards. And when it bends, this corner over here moves forward by just about 30, 40 nanometers. Okay, nanometers we're talking here. But if I keep on repeating that process, you will see that small movements become a large scale movement. So let me show you schematically what's happening. So I'll run this video here. Okay, and you see what's happening. I'm going to repeat this a few times because it's a very short video, but just watch what happens to the top and the bottom. See, the top moves down, and as it moves down, its front part actually takes a forward step. So, where am I? Close. So I've lost myself. Why have I lost myself here? Da, 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 da. Okay, sorry about that. I think I was trying to do these. Some of these are old recordings, so I had to make some adaptations to them. Okay, and it might jump around a bit. So let's see if we can avoid that. So let me move to the next slide. This is an actual image, a recording of this micro actuator. Okay, we call it a three-stage actuator because these three squares represent each stage. And now if I click on this, you can see that it moves forward. Okay, it's moving forward at an average velocity of 20 microns per second. Okay, but you can clearly see that it's moving from 0 up to 900 microns, almost 1 millimeter. Okay, so this is one of our first micro actuators. So when we built this type of device, the first thing we thought was, well, this is a great device, but how much force does it produce? Because if you have an actuator, your actuator is trying to do some work. And usually that work is it's trying to position something, it's trying to pull something. So we built this simple structure here. It's a test structure to try to measure the force of the actuator. And what you see we have over here what's called a box spring. It's a spring. And when this actuator operates, it pulls and stretches the spring. And when the equilibrium is achieved between the force of the actuator and the restoring force of the spring, we can actually measure the displacement of the spring. And if you know what is the spring constant, and we actually work out the spring constant by calculation, if you multiply the spring constant by displacement, that product has units of force. So you see here we have a diagram which shows different actuators from 1 plate up to 4 plates. Okay, here we have worked out the force, and here we have worked out the voltage that is actually applied. So you can see that, for example, if I can get something like 900 micronewtons of force out of a 4-plate actuator, if I apply like 200 volts to it. So this gives me some understanding of what kind of objects I can push and pull using these actuators. Okay, so moving on, this is the same poly-MEMS example. This image over here is of those micro mirrors I showed you. It's this micro mirror what you saw before, but now I'm looking at it through a microscope, and I'm looking at it by using a video. And you see in this structure, we have 9 microactuators, 3 by 3, 9 microactuators. And this round structure here is a reflective mirror, okay? So at the moment, this mirror is lying horizontally, okay? Now, if I click this slide, you see what happens, okay? You see how this mirror has now been pulled into the vertical position. So in doing this, we have applied this actuator to, yeah, okay, now I know what I'm doing. I need to pull this down and close that. Okay, so we've used this actuator here to pull up this mirror. Okay, so it's doing something functioning. It's doing something functional. The mirror is going from horizontal to vertical. This side here shows you that these devices don't necessarily have to move in a straight line. If I click here, then you can see that I can also make a circular motion using these types of actuators. So they are not always linear, they can also be circular. Okay, so quit that and I'll close that. And I'll move to the next slide. So those are some examples of the polysilicon process, and there it requires a really good understanding of what you're doing. Now, this is SOI MEMS. Nowadays, it's called SOI process. And I believe in last year, when those of you who were trained on the MEMS course, I believe you were trained on using this process, SOI process. So I won't go through all the details. I just want you to look at F over here in the bottom right. Okay, and you see that what this allows me to do is it allows me to create a silicon structure which is completely suspended. It's suspended because using back etching process, I can remove all the underlying substrate material. And then on the top side, I can put in different types of materials. Usually we use metals. So this gold structure is what's called kind of pad metal. There's pad metal and there's blanket metal. But these are definitions which I think you will have probably understood through your training. So what do we do with this type of process? Here's one of the devices we made early on. Okay, it's again a micro mirror because, as I said to you, our interest is in optics and photonics. This is a circular micro mirror. It's 800 microns in diameter. And on this side over here and on this side over here, we have what are called electrostatic actuators. Okay. And the thing about electrostatic actuators is that you have one set of actuators is connected to the structure. One set of actuators is connected to the surrounding silicon. So you have, again, like a capacitor, and that capacitor generates a force within it. So here we have done two simulations. The diagram on the top here shows the first modeled tilting mode of the actuator, and we modeled it to be 11 kilohertz. And when we measured it, it was about 10.2 kilohertz. Okay, so there's good agreement over here. And the tilting is around this axis over here. So it's tilting from side to side. The second mode, we call it well, we'd say it's a second tilting mode, okay? It has a 42 kilohertz model, and when we measured it, it was 41.7 kilohertz. So again, there's good agreement. And here you can see the tilting is almost follows this S shape, okay? So you can see how this mode is quite different from this mode over here. Just checking my time here. Okay. So this is a different variation of the previous structure. Actually, the only difference is that instead of having a circular mirror, we have got a square mirror over here. We wanted to understand what is the effect of having these square corners on the overall design and the overall production of the structures. This and the next image I'll show you are really very interesting. We have a kit which is called a dynamic profiler. Okay, and with this equipment, you can put a MEMS device within this equipment. Okay, and you can operate the device and you can actually visualize and measure the dynamic behavior of the device. So I need you to understand that what this image I'm showing you now, this is not some simulation image. This is actually the device sitting in the equipment, and this is data which we captured. So if I click this here, okay, You see how this device is moving from side to side. I hope you can see that quite clearly. I'll maybe just run it one more time just to show you. Okay, so these are actual measurements that were made on that device at that particular frequency. And if I move to the next slide, this is the second mode of that structure. The same device, just taken from a different angle. Now we're at 37 kilohertz. And if I click on that, you'll see that now it's moving in a different mode. Okay, it's moving in this S shape that I showed you before. Okay, so that kind of equipment makes it's an important facility to have in order to measure the dynamic behavior of these devices. Okay, so we've done many of these analyses. What you find is that sorry, let me go back. For what we call our small mirrors, you have these mirror angles. When they're tilting, you have plus minus 14 degrees in first mode, you have plus minus 2 degrees in the second mode. And then the larger mirrors give you different behaviors. Large mirror with frame, I don't have time to discuss with you, but they also give you different behaviors. So these are the typical characteristics of such a device. This is what happens if you take one of these devices and you operate both axes at different frequencies. So what we have over here is one axis is being driven at 10.25 kilohertz, and the second axis is being driven at exactly 4 times that number. So 4 times 10.25 is 41 kilohertz, okay? And when you do that and operate that, what you're seeing over here is we are shining a laser beam onto the mirror and then bouncing it from the mirror onto the screen. Okay, and I think many of you will have seen these types of images before. These are the Lissajous patterns, and it just shows you how the optical beam can be deflected and given this kind of shape and onto a screen. And you can move it fast and slow depending on what kind of frequencies are applied. Okay. This is a different version. I think I have time, so I'll just show you what we call a complex Lissajous figure. This is much more complex, and you see there are so many crisscrossing and patterns generated with these Lissajous figures, and they are actually very useful. They can actually help you to generate certain types of images. So here, one frequency is at 6.5 kilohertz, and the other frequency kind of varies over this range. Here, we were very interested to see how our scanners behaved with infrared radiation. So, infrared is not visible to the human eye. We used a high power, 500 milliwatts laser, is actually quite a high power laser. And we did some post-processing. So what we did was we put silica and niobium dielectric stab, and we deposited that on top of our micromirrors. And these silica niobium stacks have high reflectivity for infrared wavelengths. And we wanted to see whether these infrared wavelengths, these high power wavelengths, do any damage. And so far, it looks good that we can scan these infrared beams over here, and the damage, in fact, there is no damage to the actuator itself. So that's very good. It means we can work in the visible, we can also work at high power in the infrared. This is a different type of scan pattern I'll show you. It's a different kind of actuator. It's what we call a thermal scanner. But interestingly, you can see we can do quite interesting movement and shapes with this type of structure. It's a different design. It relies on heat rather than electrostatics. And then working with the same design, the same kind of actuator, I can create some more complex pattern. I have these kind of spiral patterns that we can generate, as you can see. This is all in the visible, but of course it can be done in the infrared as well, okay? And here is if I use a camera and just extend the exposure and look at those spirals, you can see here we're getting spirals. We can here also get concentric circles. So it's a way of generating patterns from the laser beam in a simple way. Now, you can be more complex. And you can use the scanner, which I showed you, and with its pattern generation, but you can use that with a modulated laser, which you can switch on and off, and you can really get some interesting patterns with it. So this is a lab view environment we're working in over here, and we created a program to allow us to draw real objects. What's happening here? The laser beam is scanning from left to right. So imagine it's scanning as my arrow is going left to right, and it comes back left to right, and that's fine. But then at this point, what we do is we switch off the laser. So now there's no light. So if there's no light, it means there's black over here. So during this period, the light is switched off. But then over here, once again, we switch on the laser and keep scanning. So if you coordinate between your scanning and switching the laser on and off, you can start getting some really interesting patterns. You end up getting laser projection. So whether you call this number 5 or letter S, you can see that this is the letter S. I hope that's clear to you on your screen. And you can then make it more fun. You can make it more complex. So this is the same lab view environment. This is the design we wanted to create. Okay. And then you can see by just putting that design here, you can project that design here. It's done with a red laser. Okay. And then here we can even create here a figure of Homer Simpson. The thing to bear in mind is that with the laser, you can also get grayscale because you can change the intensity of the laser beam. So not only can you switch a laser on and off, okay, but you can also change the amount of light coming out of the laser. You can make it very bright, fully on. You can make it half on, quarter on, all the way to 0. Okay, so if you are able to change the intensity of the laser and coordinate that with the program, you can even get these gray scales. Okay, and it may not be so clear in the screen over here, but if you can just squeeze your eyes, just look through half closed eyes, you might just be able to make out this pattern of Homer Simpson here. Okay, so that was referencing the two types of scanners. They were electrostatic and they were thermal scanners. But we also create what are called hybrid scanners. So what is a hybrid scanner? So with a hybrid device, what you can do is you can take two different actuation modes, okay? So I've already mentioned to you electrostatic actuation while I've been talking. I've also mentioned to you electrothermal actuation while I've been talking. And what I'm saying here is that I can create a device in which I combine electrostatic actuation as well as electrothermal actuation and try to get the benefits of both technologies, okay? With electrostatic actuation, I actually have large scan angles, but I have to have high voltage and a complicated algorithm to drive it. With electrothermal actuation, I get large scan angles also, but low speed, but I have low driving voltage and simple control. But the electrothermal does require higher power conversion. So these are the different characteristics of the different different actuations. So here we have here's one example of a hybrid scanner, okay? So in the middle over here, I have the round disc, which is the mirror, okay? And this side here and this side here, I have what are called thermal scanners, electrothermal scanners, okay? And they move up and down in the plane. And then down here, also connected to this same micro mirror is the electrostatic drive. Okay, so I have a thermal actuator, thermal drive on this side, and I have electrostatic on this side. It means I'm using two actuation schemes into this one single device. So what does that give me? So here are some of the simulations we did. So you can see that this device has a symmetry over here, which is, you can imagine it's symmetrical through the center axis over here. So everything is nicely balanced out. And so the thermal axes are symmetrical. If you look at the what I call the second mode over here, which is this image here, it's not so symmetrical, and you can see why. Because if you just even look at this object, there's no symmetry. I mean, there's one axis of symmetry here, but there's only one axis of symmetry. So these deflection profiles are slightly offset, but they're still functional. So I can still use this resonant mode to scan in one direction, and I can use this resonant mode to scan in the orthogonal direction. So that is about those particular devices, which is mainly the scanners. So I'm just taking a pause here to check how my time is going. Okay, I've got about 10 minutes left. So this device is a variable focus micromirror. Okay, and it's actually a remarkable device. It's simple and remarkable. You see what it looks like over here. It's basically a suspended silicon device, a suspended silicon disk with gold on it. And then it's connected by 8 springs to these pads. That's all. This is made in SOI. And if I measure this device, you see that its profile in either X or Y direction looks something like this. It has a small curvature. But I need you to be very careful when you look at this graph. Bear in mind that from left-hand side to right-hand side is 1 millimeter, which is 1,000 micrometers. Whereas from this point here to this point over here, from this point here to this point over here, it's only 5 micrometers. So this device is 1,000 micrometers in that direction, and it has a small static deflection of 5 micrometers. Okay, so it's essentially flat. What happens is that if I pass an electric current between these electrodes, I begin to heat up the device. And when this device heats up, because of differential thermal expansion between the gold and the underlying silicon, the curvature of this device changes. And that's very interesting, okay? So you see, for example, on this graph over here, I'm applying electrical power, and I'm applying it through different combinations of those electrodes, pads. And you see the curvature is changing. Here I have something like 23.5 millimeters radius of curvature, and that radius of curvature changes to something like 29.5 millimeters radius of curvature. So I can actually control and modify this radius of curvature of this device. And that makes it very, very useful for imaging applications. I don't have time to discuss this slide, this right-hand graph, so I'll just carry on. What does it allow me to do? If I can control the radius of curvature and I use a reflective imaging system, then you see, I can focus on an object which is nearby. So here I'm focusing on this pencil, this red pencil, which is 23 millimeters away from me. Then I can apply electric current and the mirror adjusts its focus. And now I can focus on this other pencil, which is 235 millimeters away from me. Okay, so I can focus from here to here. And what is remarkable about this is the quality of the image and the fact that these MEMS devices are there. The aberrations are incredibly and unbelievably low. And so this is a very, very interesting focusing arrangement. If I just click on this, you can see what we're doing. It's maybe a slow video. So I'm showing you on the left-hand side. You can see we are focusing in and out. So this is focusing a laser beam, but on the right-hand side, we are focusing onto some specific objects, namely the tip of a pencil. So we have now my next object, which I want to show you. This is an on-off switch, okay, for fiber optic applications. And what you see is this vertical line is actually an optical fiber, okay? So, and normally I would place an optical fiber on the other side as well. And what I want to do is I want to transfer light from first fiber into the second fiber, which would normally sit over here, okay? So I want to align the fibers and I want to unalign the fibers, okay? So just watch as I run this video, watch what happens, okay? So look at the sequence. The teeth open the actuator pushes this optical fiber, and then the teeth close. And now everything is locked into place. So I've displaced the fiber and have locked it into position. Now I can apply the voltage once again to these devices over here, the teeth. They open and the optical fiber comes back. Okay, so you see, I can displace the optical fiber to the left, to the right, by using the actuator and by using these teeth, which lock onto the actuator when I decide I want to do that. This structure actually shows you in more detail some of that actuator side. These are some of the teeth. We call this a vernier actuator. And in this actuator, we have a whole sequence of teeth over here. And we have these spring-loaded teeth and the teeth on the moving part. And what you find is that some position, the teeth on both sides come into alignment. And when they come into alignment, this locking takes place. And then the actuator is locked in its new position. Okay. What's interesting about this is that here we've done some measurements. What we have done is we have 30 latched points right over here in a space of 18 microns, okay? Which means that we have been able to make 30 fixed points within 18 microns. So basically, each fixed point is less than half a micron. It's around, no, it's a little over half a micron. It's 2/3 of a micron, about 650, 660 micron. Not microns, nanometers, okay? 18 divided by 30, convert that into nanometers, okay? So here is the interesting thing. I'm using micron technology, which gives me structures which are 3, 5, 10, 15, 20 microns, and yet I'm handling with a precision of 600 nanometers. Okay, so this is what the vernier latching process allows to do. So next, I want to talk about the piezo MEMS process. Some of you may have heard about the piezo MEMS process. Again, it's been around for a while. I just want you to focus on slide F, this image F over here, down here. This is exactly SOI MEMS, so one difference. The difference is that the fabrication process allows you to deposit aluminum nitride on the surface of the device, okay? And those of you who know that aluminum nitride is a piezoelectric material, so if you apply voltage to it, it'll displace, it'll deflect. If you apply AC voltage, you will get AC vibration out of this aluminum nitride film. Okay, so it's a way to also actuate. It's a way to also actuate devices. So I'll show you one device we've made. We built many devices. I'll just show you one of them. This one here. So this is a high frequency piezo scanner. Okay, and this diagram is indeed complex because we were trying to do 3 experiments on one device. Okay, in order to get leverage out of using this technology. But essentially what we have in this device is around here you have an actuation which is based on aluminum nitride, okay, which is a piezo material. In the center here you have a scanning mirror, so this is a gold, this is in fact an aluminum coated mirror over here. And then on the sides over here, we have different actuators, but the ones I want you to concentrate on is what we call actuator 1, single track actuation 1, single track actuation 2. And what we're trying to do is we're trying to see that if we apply heat to this actuator, can this heat be transferred to this micro mirror device, change its temperature, change its stiffness, and therefore change its mechanical frequency, its resonance frequency? And the answer is, in fact, you can do it. So here's some data we have. So here's the device, okay? We have this mode over here, what we call it the piston mode. The device is moving up and down. We have what we call the orthogonal tip mode, and that has its resonance frequency here. And then we have the tilt mode, which we have over here, this third mode. And you see that for each mode, we have the modeled frequency, okay? But what you see is that in some of the modeling, the compatibility is good, but in other modeling, the compatibility is actually not very good. So look at this one over here. This mode, the piston mode, we expect to have 154 kilohertz in the model, but it's only 130 kilohertz in practice. This second mode, the orthogonal tip mode, we expect it to be around 220 kilohertz, but look, its real measurement is around 140. Third one is this. So this third mode over here is what we call a tilt mode. And the tilt mode is the one the agreement is the best. In theory, we expect 180. And in fact, in practice, we also measured 180. And the question is, why is this difference? Actually, you can see even in this graphic, you can see yourself what's happening. Look at this one here, 180. In this device, in this mode over here, the only movement is of the mirror itself in the center over here, and all the structure around the side remains static. So when the structure remains static, the whole mechanical problem becomes less complex and the compatibility is very good. Let's go to the other end. Look at this mode over here. So this mode here corresponds to this measurement, 140 against 220. Huge difference. Why? But look why. Because here in the model, the whole structure, the surrounding structure over here, which is the actuation structure, the micro mirror itself, everything has got various degrees of movement. There are non-linear effects taking place over here. There are effects called spring hardening, which are taking place over here. I won't go into the details of that, which means that the modeling does not actually represent the physical reality. And so the difference is high. And then if you look over here, what I call the piston mode, in the piston mode, you can see these colors are less, which means the structure around is moving less. The main movement is over here, but there's still some movement around the side. That's why we measure 130 versus 154. Okay. Very quickly, this is how the frequency tuning took place. So I said we apply thermal effects in the way I described a few moments ago. And you can see that for one of these modes, the tip mode, we can tune the frequency from this point here all the way up to this point over here. These are relatively small changes, but important. And then in this tilt mode, we move from this frequency 180 up to maybe just near to 181. Again, a relatively small change. Thing is that these small changes are quite important because they allow you to take devices, they allow you to tune their frequencies so you can operate these devices together in a certain way for more complex operations. Okay, so here we are, right on time. Last comments and my last few observations. First, this is a lesson. You do not need to have your own fab and full processing capability to conduct research in MEMS. Okay, you don't need to have that. Two, if you are fabless, it allows you to access a wide range of technologies which you do not need to maintain. So in a way, less is more. You have less in your own institution, but you have more access to the different foundries. Three, is that you can post-process dies from a fab using your own custom material. So we were able to do that. We put in various silica niobium layers to create multi-layer dielectrics, but there are other kinds of materials you can deposit if you wish to do that. Next is that it would be really good if we had more multi-project wafers from fabs around the world. The reality is that multi-project wafers don't make a lot of money to the people who own the fabs, so it is less priority for them because of these types of reasons. Finally, with multi-project wafers, you need to think more deeply. You need to be creative how you can differentiate your work from other people who are using the same processes. But I hope I've been able to show you in the last period that you can create devices, you can still do a lot of research, and you can go ahead and publish a lot of material. So I just want to thank all my friends and colleagues here who worked with me for a very long time in the past. And I thank you for your attention. So Vida, it's over to you now.
Thank you so much, Deepak. This has been wonderful, especially what you concluded made a lot of difference to me because of the MEMS training initiative that we took from Sensors Council. It just shows the impact you can have from that kind of training to people who don't have access to fab. And it's wonderful to see the great work that you have done over so many decades from that perspective. And to also know you as a researcher, I have known you more as the Sensors Council president all this while. Now I know you more as a researcher. That's great. I request all the audience to put your questions in the chat box, and we can take from here the question and answers. So we have a question there. Deepak, you can
Vida,
see the chat.
read it out so I can
Okay.
leave my screen on, okay?
Okay, sure. What is the major advantage of using optical base switch over normal cantilever MEMS switch? That's the question.
The applications are different. I think with an optical switch, you have with an optical switch, you are kind of diverting one or more beams of light. Okay. When you talk about a cantilever switch, I don't know whether you're referring to photonics again, or you're talking about different types of, whether you're talking about electrical signals, okay? Because cantilever switches are good for if you're trying to switch on and off an electrical voltage, but the optical switches really work only with lasers and light beams.
Any other question from anyone else? I have a question, Deepak. So, yeah, Hamza, please go ahead.
Okay, sorry. Thank you very much, Deepak. And I think it's really fascinating to see some of the images you showed us because I've seen these in different text as well. So excellent work. So my question is again about, you said that you can go fabless, but in terms of testing, what do you think? You still require specialized equipment.
Yes,
and
definitely.
how expensive that can be.
Yeah, exactly. So this is our model. This is our models, but many people have followed these models. So you first of all need to have the design tools themselves, okay, and that's software, okay. So that's straightforward enough, okay. Then fabless means you don't have the complex facilities. You may have simple etching facilities, deposition facilities, but if you want to do something really, really complex, then the kind of facilities that are available in most universities, don't allow you to reach to that level. Okay, but you're absolutely right about the third point. You need to have a well-equipped testing facility. Okay, and over the time I have been at my institution, and many of my friends around the UK. We spend our resources to get the testing equipment because that testing equipment is actually very vital. And for example, the dynamic profiler, I showed you the images from that. Without that dynamic profiler, we would have been completely lost. We'd have no idea, what's going on. So if you have the resource, then you need many devices. You need packaging, you need wire bonding, you need actual testing. Preferably, you need non-contact testing. So the dynamic profilers, they're optical based, and they're the kind of equipment which are accessible. Certainly, today's dynamic profilers are far more advanced than the ones we bought even 10 years ago. Okay, so that technology is moving forward, and almost nowadays you put the device in, go away, have a cup of coffee, and the measurements are done when you come back.
Thank you, Deepak. Lenin, you can unmute yourself. You're a co-host, and you can ask your own question that you put in the chat box.
Okay, thank you for the presentation. My question was on ASAJU. Are LaserJU patterns used in evaluating the performance of resonant scanning systems, and how? Yeah.
So the listed use, we don't use the listed use as a means of measuring the performance of the system, because there are tools which are much more accurate, such as the kind of tools I just described a few moments ago. The listed use is there for two purposes. Number one, it's to create nice pictures so that I can show people like you these nice pictures. But number two, you can actually use listed view images by synchronizing the listed view pattern with the switching of the laser, and you can actually project images. So the listed view pattern, if you like, covers the whole field of view. And by synchronizing the switching of a laser on and off, as I showed you also, that is a more significant purpose of the listed view. It's not more for testing, it's more towards the application.
Bala, you can also ask your question.
Sir, it was a very nice talk. Thank you so much for that. I was just curious about what is the minimum displacement that can be measured through this dynamic profiler which you showed, like
Yeah,
not even to visualize. Yeah.
It is every couple of years when the next model comes out, it comes out more and more. So the dynamic displacements are in fact below a micron you can measure. Okay, and in fact for us it's the other. We want to go the other way. Sometimes the displacements we have are in fact quite high. Okay, it may be several hundred microns. Okay, it may be it may even be a low number of several hundred nanometers, or it might be low number of microns. Okay, and you want to have the instrument which has a large dynamic range. Okay, but they're extremely sensitive, and you can easily measure. You can measure displacements in the order of nanometers.
Okay. Okay.
And I think I have one
And
last
one more.
question. Sorry,
I'm
I'll just
sorry.
ask mine and I can come back to you.
Yeah. Sure.
Deepak, you said about the advantage of having a fabless thing, but there are disadvantages as well because you have to follow the design rules and the constraints that come with that. So how challenging has it been for your students and for your groups to make sure that within the design rules and constraints, they have been able to come up with such excellent results? How have you managed
Well,
that?
it is, as I said, it is, I think, let me give you an example. So I showed you one of the first devices we made, which was the actuator, the SD, what we call the SDA, the nano-stepping actuator, okay? And as soon as we saw as soon as we could see the basis of the nano-stepping actuator, we saw that we have done this design. There are other people who are doing the design, but immediately this question came. This is great, but how much force does it produce? Okay, so no one had thought of that question at the time. Okay, and so this is the thing, Vida. It's never easy because everyone has the same tools, so you have to ask a different question. So when you ask the question, well, we are engineers. We are using these actuators to apply on some kind of structure, and just by basic mechanics, what is the first thing I need to know? I need to know force. Okay, so this is it. You have to look at what there is. You have to think, well, what is the unanswered question? Okay, and then find a way to answer that kind of question. And now I could easily take that question forward. I could say, okay, now I know what is the force that is produced from the device that comes to us from the foundry. Now I can coat the device with my own coating, some proprietary material I want. Because as you can imagine, the behavior of the device depends on friction. It depends on everything coming together in a particular way. So I can change the problem and I can say, okay, I can begin now to give comments and research on the surface quality of materials I deposit by simply making the actuator walk across the surface and make some measurements of that surface. So it's never easy, because one thing I have always remembered, there are a lot of smart people out there. Okay, you just have to keep half a step ahead.
That's true. Yes, Bala, you can go ahead. Sorry, I cut you.
Sorry. So I was just curious on this resonance tuning which you are showing finally with the electrothermal actuator stuff. So what's physically happening there, and how are the resonance is actually tuned? Like, and the control is so very nice that, I mean, you can tune it in very small frequency steps. That's what I was.
So I'll tell you that. So first thing is that if you look at that structure, it's been published, so you can actually find the full paper.
Okay.
If you look at that paper, if you look at the work there, first thing we did was we were trying to avoid physical contact. Okay, so when the tuning element is actuated, it is physically close to the rest of the structure, but it isn't mechanically touching it. So what it means is that we are heating that structure. If you go back and look at that structure, you'll see that there's a very sharp point over there. And there is a very, very narrow air gap between the thermal actuator and the physical device itself. And you know that in the macro world, you think that air is a poor conductor of heat. And yes, in the macro world, that is very true. But in the nano world, if you have a very, very narrow gap, the heat can quite easily transmit across the air gap. Okay, because it is a submicron air gap or a micron air gap. So what's actually happening is all the heat that we are applying to the to the actuator itself, some portion of it is actually transmitting into the structure itself. It's heating up the structure, and when you heat the structure, you know you have dE by dt, which means the Young's modulus changes with temperature. Density changes with temperature. All these factors change with temperature. It means finally the stiffness of the structure changes with temperature. And then the stiffness dictates what is the resonance frequency.
Yeah.
Okay.
Yeah. That's very very innovative. Yeah.
Yeah.
Thank you, Deepak. We are run over 5 minutes, but it has been amazing to have you. In fact, MEMS is an ocean, and you have brought the photonics sensing and MEMS together through your talk. And one aspect of MEMS kind of gets covered by your talk from the optics and photonics point of view. Going forward in this series, we'll have the other domains of MEMS sensors also getting involved. But it was wonderful to have you and to begin this series. And request all the audience to stay tuned for the wonderful line of speakers that we have for them in the future.
Yes,
thank you so
thank
much.
you very much, Vida. Thank you very much. And I want to echo what Vida just says. This is an amazing program that Vida and our other leadership team have come up with. I think it's one of the best things we've done for a long time. So please move on to the next stage and listen to these webinars from other prestigious people, and a lot, I'm sure a lot will be learned. Okay, thank you, Vida, to you and everyone who's supported this whole initiative.
Thank you, Deepak. And these all the webinars are available going forward in Sensors Council YouTube channel. So please subscribe to the YouTube channel, and you will be getting notifications as we update that. Thank you so much, and have the nice rest of the day.
Okay, thank you very much. Bye, everyone. Bye-bye.
Thank you all. Bye-bye.